Hello, my name is Birring, and this lecture will be on remote field eddy current testing of carbon steel tubes. First of all, we need to understand that the remote field principles are totally different than the conventional eddy current testing. So here, let me explain you how this remote field works. In the remote field, this is how it works. We have a transmitter here, and the transmitter produces what's called a direct field. So this is the area of the direct electromagnetic field, and this region, your ID field is higher than the OD field. This is the ID curve, and that's your OD curve. So here, your ID electromagnetic field is significantly higher than what's on the OD, but then this ID field drops rapidly here, sharply, and it comes down to this transition point, and then it picks up. But from this point onwards, the OD field is higher than the ID field. Now, going forward from this point, they both become linear. The OD field and the ID field are both linear, just like the way it's shown here. And beyond this point, we have what's called the remote field electromagnetic field. So all the remote field electromagnetic field is done by placing the transmitter here and the receiver at this point, which is past about 2 times the ID of the tube. So this is how it's actually done. So we have the transmitter, receiver, and the receiver is placed beyond this point, so after about 2 times the ID of the tube. And this is how, and at this point, so the way it works is the electromagnetic field is here, it diffuses from the ID to the OD, then it transmits on the surface right here, and then it back diffuses from the OD to the ID. So now if there is actually a wall loss, this time, the time actually which is taken here, or the phase which is received by the signal by the receiver will be affected. So just make sure that this remote field, we have to keep the receiver more than 2 times the ID of the tube. Now this is how it's done. This is this is a calibration tube, and I'll show you what it looks like. This is the actual tube, and in this case we have this is 3/4 inch by 083. There is a support plate here, which actually is like a ring here, carbon steel. And then what I have is a short flaw, which is like this one here, concentric, 360 degree, 40% deep, all the way 360 degrees. And then I have a long flaw here, which is from here to there, which is 60% deep on one side, but it's actually only 180 degrees. So we have we should get 3 signals from these points. So now I'm showing you a probe here, RFT probe, and in this probe we have a transmitter here and a receiver here. As you can see, they are separated, and this separation is about I would say 3 to 5 times the diameter of the probe. So whatever is the diameter, this is how the manufacturers will make it. So it's not right next to each other. They actually have a separation from here to there, just like I've shown it from here to there in this picture right there. So now when you apply AC, in this case we have a tube which is 3/4 inch OD by 0.083 inch thickness, and I am applying 400 Hertz AC, remote field AC, 400 Hertz. Now remember, in eddy current we are working in kilohertz, and in remote field we are only working in hertz. So we're going to pull this, and first we're going to see this concentric groove, which is 40%, 360 degrees, and this is how it works actually. And then we have the support signal, and then we will have 60% deep, 180 degrees. So the signals which we will receive are going to be displayed on the screen like this. The support plate signal will be something like this, and what we do is we rotate this signals so that we bring the support plate to 0 degree. So when we bring this to 0 degree, then the 40% at 400 hertz on this tube will show up something like this. Now, what you will notice is that the 40% produces two signals, and the two signals are because as we pull the probe here, first the transmitter will see this groove here, and then it will balance out, come back to zero here, and then the receiver will see the groove again. So one could say that this signal, first signal is from the transmitter and the second one is from the receiver. So then it balances out again, and then we see the support plate which is right here, and we set it to 0 degree, and then we keep pulling the probe, and then the transmitter, when the transmitter is here, then it's going to see it, and the signal is going to go up to here, and then both the transmitter and the receiver will be underneath here, so like this, and when both of them are underneath, then the signal is going to go, and it's going to go to this right here. So we call this as the long flaw because it's longer than the length of the probe. So here the signal, when the first coil will see it, let's say we are here, and let's go back here, and I'm going to draw the probe again. So when let's say the probe is here, and this is the transmitter, this is the receiver. So the transmitter will see it, it will go up here, transmitter, and then when both the transmitter and receiver are underneath the groove, the signal is going to go all the way up to here, and then the transmitter is going to come out, it's going to come back here, and then it's come back to zero when you have pulled it out. So this is how the signals are going to look like. The only issue with the remote field is that it's basically good for wall loss, and I would not I'm a little bit concerned about using remote field for detecting small flaws like pits and holes, and the reason being that they produce a very small signal, something like this. So if you have a small hole or a small pit, it's going to be like this. And as you can see, when you're doing the real inspection, what will happen is that this signal could be shadowed by the noise, because these carbon steel tubes in the actual field are not going to be like the calibration tube I showed you. They will have oxidation and rust on them. So you actually could potentially have noisy signals here, and when you have noisy signals, then you will have defects like small pits and small holes. Now once we are all done, then the machine which is here, first I'll show you the support plate, and the support plate is here. We made it 0 degrees, and this is the short flaw, so this is how the remote field signal will look on the screen. I will just show you the support plate first. So the support is here, which is right here. We make it at about 0 degrees, not about, but actually 0 degrees. So then I will show you the short flaw, and first the transmitting coil will see it. It comes back to the balance position right here, and then the receiving coil is going to see it. So you'll see it 2 times, because this flaw is actually shorter than the separation between the transmitter and the receiving coils. So this is what I was calling it the 40% D flaw. And then we go to the support plate, and then we have the long flaw. In this case, as you can see, the signal will rise, and it rises here. The first coil will see it, and then the second coil will see it, and then it comes back to the 0 position all over again. So if you want to see all of that, you can see the support plate and the signals. So the support is here, support here again, the first coil, and then the second coil, and then back to the 0 point. Overall, it will look like this. Here we go. So anyway, and then we have the depth curves. So we make a depth curve which will look like this, and they will actually be something like that. That will be the depth curve, and we use the depth curve. If we see any flaws, then we use them to estimate the depth of the flaw. So in conclusion, just remember, its technique is different than eddy current testing, conventional eddy current testing. It's not sensitive as sensitive to the small pits and holes as the conventional eddy current testing. So the remote field eddy current is a good technique, provided you know the limitations of this technique. And the main limitation of this technique is that it's actually will be limited to wall loss, general wall loss. But once you start looking for pits and holes that are smaller than 10 millimeters, the signal will drop to very small value, and you may not be able to see it easily because it will be covered up by the noise, or the signal to noise ratio will drop. So thank you very much and have a good day. Thank you.